Hey there, everybody. Welcome back. We just had a nice little theorem in the last section that had 3 parts. And proving it would be a pain to do. So it's a little it's impossible to evaluate every single piecewise curve. So let's just introduce some new ideas that'll help simplify finding conservative vector fields. So we need to know what a simple parametric curve is. It's a curve that doesn't cross itself between endpoints. It may or may not be closed. So this is a simple curve. And something that does this is not simple. Okay, it crossed itself. And I should show it going along the curve like that. There you go. So that's a simple curve, doesn't cross itself. And when we want a simply connected region, it has no holes inside of it, is the big point. It doesn't, a simply connected region does not capture any points outside of D. Visually, this one is simply connected. This one, I could do a closed curve like this and start here and go around, and it captures points outside of it. So this is a multiply connected region. And we'll see how we deal with this in 15.4 when we have holes in our domain, our region. This is called multiply connected, not multiply, but multiply. And so what are we going to do to test conservative vector fields? You're going to see in this video and the next video, this all boils down to whether or not the curl of the force vector field is 0, or effectively the 2D version, the rotation matrix is 0. So we'll see that in the next 2 parts. So let's just start with the 2D version of this. And so the curl in both of these, the curl or the rotation is just the determinant, is a word you'll learn in linear algebra, determinant of a matrix. And we're going to show they equal 0. Okay. So let's look at 2D. If f of xy and g of xy are continuous on an open region D, they both have continuous first order partial derivatives, and f, which is composed of f in the x direction, g in the y direction, is conservative on D, then df dy equals dg dx at all points in D. And conversely, it goes the other way. If D is simply connected, and this property holds true for all points in D, then f is conservative. So starting with conservative leads to that. We're starting with that leads to conservative. Why? This does stem kind of from doing the definition of what df dy is. If I take df dy, it's really the partial with respect to y of the ddx of phi. Because remember, we've got f is the gradient of phi, which is d phi dx, d phi dy. So f is d phi dx. So we got d dy of d phi dx. This gets us d squared phi over dy dx. Using Clairaut's theorem, we can switch around the dx dy, separate this back out, and we've got the partial with respect to x, the partial with respect to y of phi. This is just the partial with respect to x of g. So we've shown that df dy equals dg dx. That wasn't the curl or the determinant I was telling you about. That's just one way of showing it. If we look at that rotation matrix I was telling you about, we've got our gradient across the top, ddx and ddy, f and g. I've got dg dx minus df dy, and I said the curl or rotation had to equal 0. So if it equals 0, we move the df dy to the other side. We get dg dx equals df dy. That is our conservative field test for two space or two dimensions. Okay. This scales up to 3D. I was going to do this in another video, but this scales up to 3D. Let's do our curl of f. So I've got ijk of ddx, ddy, ddz, fg, and h. If you write out the determinant of this, is what it's called when we do the cross product. The cross product is a determinant. Again, linear algebra term. We've got dh dy minus dg dz for I. Negative j will be dh dx minus df dz. And k will be what we had for the rotation matrix, dg dx minus df dy. So if the curl of f equals 0 for each of those, we set each of these components equal to 0. And we get the conservative field test for 3 space. Each of these has to hold true. dh dy equals dg dx, df dz equals dh dx, and dg dx equals df dy. If those all hold true for 3 space, again with f equaling f, g, and h, then we have a conservative vector field. Something else that we've done in this chapter that extends to 3 dimensions was the f.dr. It scales up to 3D also. So if f.dr on a closed loop, not on a closed loop, this just that this is the definition of f.dr. We've got phi at 0.1 minus phi of 0.0. And it scales up from 3D. That's it for this video. Peace.